Wait, now I lost the button. What is this? You can still hear me?
Hi, Thomas. Yes, we hear you.
Okay, because I lost somehow the Zoom. Okay, this will take 1 second. There it is. Okay, sorry. Because I'm on a Linux desktop and I don't always fully understand it. So let me do a host disabled participant screen sharing. I would still, okay. Yeah.
Oh, yes. So you're the co-host now. There you go.
Yeah, thank you so much. Let me quickly remind you where we ended last time. So these were the first set of lecture notes. And I think we ended on page 12. So let me scroll to page 12. And let me quickly remind you what we had been doing. Good, so I was explaining that if you do a compactification, then there are various energy densities in 4 dimensions. And that these energy densities, they have a universal scaling with respect to what we call rho and tau. These are 2 scalar fields in 4 dimensions. And rho is, if you like, the volume of the compact dimensions in 10-dimensional string frame, or related to the volume. And tau is some specific linear combination of this volume and the string dilaton inverse. Okay, we derived the following scalings, and then I explained you the main result was the following: that if we minimize or extremize the total energy density with respect to these 2 universally present values, scalar fields, we actually were able to map this to the 10-dimensional Einstein and dilaton equation in a specific sense. Namely, it was mapping to the integrated traced 10-dimensional equations of motion. Okay, so what I want to do today is I want to start applying this in the context of the Swampland, in particular for the sitter no-go theorems and for no-goes or goes, which will involve so-called scale-separated ADS vacua. My guess is that the scale-separated ADS vacua will be the main topic for the 3rd lecture tomorrow. And today, most of what we will be doing will be related to the sitter space. Okay, so let me open the 2nd set of lecture notes to do this. And I think, yes, this is, I have to do again a share screen because I closed my file. So I open again. There we go. And before I go to this application, which is here, I still want to add one more technical aspect, which I yesterday have been glossing over. Okay. And I felt, okay, it could be a little bit important to mention this, although it's a technical side remark. What I want to mainly explain is we will see that both for the sitter space or for scale-separated ADS vacua, if they exist, that orientifolds are crucial objects. Okay, and orientifolds are a little bit tricky to deal with. They're more complicated than D-branes, and a particular property that they have, which is crucial for many of the Swampland debates, is that, you know, D-branes, you can take a D-brane and you can put 1 million D-branes on top of each other. That's a very common thing to do. Orientifolds don't work that way. So a peculiar thing about orientifolds, which I try to explain, is that they actually have a negative tension, which is very, very strange. And the string theory proof of that involves actually worldsheet techniques, where you look at the way gravitons are being emitted in the presence of an orientifold plane. But I will not discuss this. And what I just want to emphasize is how to deal with this in practice when you do supergravity calculations. And so what you always need to have is that orientifold planes live by construction, by the definition of the object, at fixed target space involution. So what I mean with this is that there is a Z2 action, so a sigma, And it's an involution, so sigma squares to the identity. Okay, a typical example would be, say you are on a 6-dimensional torus as a compact space, and I consider the following Z2 action, which inverts all of the coordinates. So imagine I have 6 Cartesian angles, so theta going from 0 to 2 pi, and I define the Z2 action, which is sending theta to minus theta for all the 6 angles. This is in fact the symmetry of the metric on a torus. And you will see that, it has many fixed points, right? So if I'm at the origin, theta equals 0, I have a fixed point. This is the same as theta equal to pi. But theta equal pi is sent to theta equal minus pi. But minus pi is identified with pi if I am on a circle of length 2 pi. So I see that I have 2 fixed points on a single circle, and I have 6 circles. So that means that I have, if you like, 2 to the 6th 6 fixed points. And these fixed points represent the position of the orientifold planes. In the particular example I was giving, they are point-like inside the extra dimensions, and therefore they are O3 planes, right? Because O3 planes would be filling 4 dimensions, and they would be point-like in the 6 extra dimensions. So for every O plane, you need to find a proper involution, which would be also a symmetry of the background space, right? But if I ever say a symmetry, it must also mean that the background fluxes have to obey this particular symmetry. But in fact, it's not just a symmetry. For the metric, it is a symmetry. But for the fluxes, it could also be what you could call an anti-symmetry, meaning that the fluxes have to be, say, odd or even, depending on the kind of flux. And so you could wonder, where do these rules come from? There are many ways of deriving them, but the proper way is, of course, using worldsheet string theory. An alternative way you could think of just looking at superalgebras and trying to understand, okay, what are consistent truncations of superalgebras so that I break supersymmetry in a consistent way. But that's very technical. It's not important for the talk. For my lecture, let me just quickly flash you the rules which have been established. So for any orientifold plane, the Neveu-Schwarz 3 form is odd. Okay, so what does that mean? If somebody says, hey, here is an O3 plane, for instance, well, then it's nicely consistent to put H3 flux wherever in the compact space. Why? Imagine I invert all the coordinates. A 3 form has 3 feet. So if every foot is being inverted, you do it 3 times, you get something odd. So it is consistent to put H flux anywhere perpendicular to, in fact, an orientifold plane. Okay. What about the Ramond-Ramond fields? That's a bit much more complicated. Okay, here is the rule. So you have to divide it depending on the kind of orientifold plane. So imagine I have O2, O3, O6, or O7. Then the parity of the Ramond-Ramond flux is given by an operation plus alpha. And what is alpha? Alpha is, yet to make it very complicated, yet another involution, which it has a name. I will not give you the name. It's just the operation on a form field that reverses all the indices. So on a 2 form, I have AB, and it maps AB to BA. So on a 2 form, that means I map it to minus itself, right? Okay, so let us apply it. So sigma of F2 is alpha F2, but alpha F2 is minus F2. And that means that F2 is odd for these orientifold planes. And I can do the same for all the higher rank forms. So if you ever need it, you can consult, for instance, this slide if you want to know what are the orientifold actions. So I really worked it out for various ranks. So for instance, alpha acting on a form of rank I is plus the form, or just maps to the form for forms of rank 0, 1, 4, 5, 8, and 9. And it's minus for the other cases. Okay, so everything together fixes this rule. This is, I think, in practice, all you need to know about orientifold planes when you do the supergravity calculations. And of course, always keep in mind that the charge or the tension of an orientifold plane, to know it, you need to count the number of orientifold planes, which you cannot decide. They are really what you could say topological in nature. So you have to really check how many fixed points does my target space involution have. And then, of course, if you really want to write down the exact numbers, like what is exactly the charge, okay, you should probably open Polchinski's book and check what are the quantized charges of an orientifold compared to a D-brane, etc. There are all these rules. I could put them in the slides, but I thought this would be too much information. Okay, you can always email me if you want to know more references that explain this a little bit in detail. Okay, this was a technical side remark, but I felt it was important to push the message to try to understand the picture. Okay, everything said so far in these lectures were technical. Let us now really apply to the theme of this school, which is a Swampland program. And I will start with the sitter no-goes. And you could say, again, I'm giving you a technical warm-up, but usually the way it works is that if you understand the technical warm-ups, you understand the full picture very quickly. And this technical warm-up, I think you might have seen last week in the lectures on compactifications. And I can only hope that I'm explaining it in a complementary way, therefore, okay? So this warm-up it is known as the GKP solution. And I will quickly review it in the language that we have developed in lecture 1, okay? So we will be considering type 2b string theory, type 2b supergravity, and the ingredients. So I'm looking for a compactification down to 4 dimensions. I will say I will use a Calabi-Yau space. Then the internal curvature is exactly equal to 0. And the fluxes that I want to put will be F3H3, and the sources will be orientifold 3 or D3 sources, okay? So I can use the formalism I developed in the previous lecture, and my energy density in 4 dimensions would look in the following way. There is a term coming from the H flux, which has this scaling with rho and tau. From the F3 flux, we know this is strictly positive, right? Because these are flux densities. They correspond to positive energies. And then there is the bit given by the source. So the O3, D3. And it scales in this particular way with rho and tau. The sign of this object, you don't know in advance. If it's 0, that would mean that there is as much negative tension in the orientifolds as the D3 branes. In the positive branes, the positive tension in the D3 branes that you put together, okay? When you find that this number has to be negative, this means that there will be more orientifold energy than that there is D-brane energy. When it's positive, it's the other way around. Okay, let us check this, okay? So my first constraint equation is that d rho of V equals 0. When I write this out, this implies that -3 times this energy density equals -3/2 times this energy must be equal -3/2 times this. The source energy density has to vanish. This is immediately a way to see that you need orientifolds, right? Because this is VH is a positive number, so this can only be 0 if this is a negative number. I learned that to get Minkowski space, well, to get a vacuum in this context, I need orientifold planes. So this is why orientifold planes are always all around. Okay. Was this easy to predict in advance? Well, we'll see. We'll see. So let me add one more constraint equation, and I think things will be become very clear. Okay. I'm asking that d tau of V equals 0. I play the usual game. I get this relation, which you understand very well by now. And I make this relation simpler by using my d rho V equals 0 constraint. And I do it by eliminating Vs from this equation. So here I have Vs, I can write it in terms of VH. I fill it in, and I get that 4 times the energy density in the H flux has to equal 4 times the energy density in the Ramon-Ramon flux. So the energy densities in the NS flux equals the energy density in the Ramon-Ramon flux. And now I can ask myself the question, okay, do I have enough information to know what would be the sign of the cosmological constant after this compactification? And I do. So the only thing I'm doing is I'm saying, okay, I write my potential energy again. and I fill in these constraints. Okay. So what does that mean? I'm going to replace V3 by VH, and I'm going to replace VS by using this equation. And here is the magic. I get an exact cancellation. So what do I learn here? I've essentially done 0 complicated calculations, right? This is essentially, you could call it child play. And I already find that if there are vacua, they will always be Minkowski. Okay, I think this is quite a strong result. And you have to know, I mean, Minkowski is quite non-trivial because Minkowski requires an exact cancellation between, in this case, a positive flux energy and a negative orientifold energy. So once you do this little game, you can ask yourself, wow, that must be very special. Can I sort of understand this more microscopically, more in detail? And you can. And this is the context of this famous paper by Giering, Skachra, and Polchinski from 2001. And this paper, I really, if you have never studied it, I advise you to study it because it contains so much of the basics that is being used in the string phenomenology literature. Okay, this is really one of the biggest classics in our field. So what I'm going to say, I'm going to explain this a little bit deeper, and I'm going to claim that in fact the potential becomes a total square. So let us go back here. If I claim that this is a total square, it's non-obvious, right? That can only be true. I mean, you have to be lucky that the powers would be exactly the powers of a total square, but that is not enough. You would also want to have that this term, US, is exactly equal to minus 2 UH times U3. Can we understand this? This is what I'm going to show you now. So my claim is that this is true because this relation holds. And to prove that relation, which seems like complete magic, I turn to the 10-dimensional picture. Okay. What do I have in 10 dimensions? So forget rho and tau. I just go back to the original expressions of the previous lecture. And in 10-dimensional string frame, this is using form notation now. And here I put a component notation if you're not so familiar with form notation. Here is the energy density of the Ramon-Ramon flux, here of the NS-NS flux, and here is the orientifold tension. Okay. Now, if I'm claiming that this becomes a total square, clearly that can only be if I know the details of this number. In other words, I would say I know how many orientifolds there would be by consistency, and that would fix the number. How do I do that? Okay, this is crucial. For this, I invoke the so-called tadpole constraint. What is a tadpole constraint? We remind ourselves first of the Bianchi identity, which is also the equation of motion for the 5 form in type 2b. And this is it. It says df5 equals h3 wedge f3 plus the source term of the orientifold. What I do now is I'm integrating this equation over the compact Calabi. And I essentially invoke Gauss theorem, which you remember from electromagnetism. If I integrate this and I say, well, this has to be a well-defined differential, then since I'm integrating an exact form over a compact space, the result has to be 0. So the integral of h3 of wedge f3 plus q delta must exactly vanish. In other words, when I integrate over the delta function, I get essentially 1. It means that the specific integral h3 wedge f3 has to be equal to minus the total number of charges. You say, fine, this is a number of charges, but how we were interested in fixing the tension. But then I use, of course, what I said yesterday. Tension for the BPS objects in string theory, which means the d-branes and the orientifolds, equals up to a sign, the charge. So I just use this. I say, great news. I'm saying, therefore, this number equals plus or minus, and I put absolute value to be on the safe side, equal to this number. And you see, this is what gives me the magic. Let us slowly do this, right? So, and I see I've made it. No, I didn't make a typo. I did it correct. So what I do, I replace this number by this integral, and I have a minus and a plus here. And now my total expression can be written nicely in terms of wedges and fluxes. And I guess you already see it now. No, let us slowly look at this together. There's a 1/2 here. There's a 1/2 here. There's an e to the minus 2 phi. There is no 1 over 2 here, and there's an e to the minus phi. So indeed, I can easily group these together, right? So, and I'm saying this is a square of a 3 form. So I can write this as star P3, wedge P3. And what is P3? P3 is exactly this combination, right? So why am I saying this is a total square? Well, this is the Euclidean metric that is raising the indices. So I essentially have P squared. And this is, the magic that I wanted to show you. So, okay, nice. If, the potential is a total square, the only way I can ever get a vacuum is if the object itself is 0. Okay, so let me go back. What I've now shown is that indeed I can write it as a total square. I already knew it was Minkowski, but here I see it again, because if a potential is a square, the only way I can have an extremum of the potential if the thing itself in the square vanishes, right? Just think of minimizing as total square, right? Then the thing itself has to vanish. So it also reproduces that the only vacuum are Minkowski. And how does the vacuum look like? Well, all flux configurations that obey this duality constraint. So this is a 6-dimensional Hodge star. It essentially says that the star of F3 goes like H3. This is known in the literature as the ISD condition, so imaginary self-dual or anti-imaginary self-dual, depending on the sign. You can wonder, where does that name come from? It's a bit of a weird name. Well, it comes from the fact that what is very conventional in the literature is to group the fluxes together into one complex form. So usually all the 3 form fluxes are grouped into an object people call G3. And what is G3? It's F3 minus, or you can also write a plus, depending on your conventions. There's an I, e to the minus phi H3. And then you can actually check, I could have made a minus sign mistake here. I wasn't too careful, that this condition becomes this condition. So indeed, this complex form is either imaginary or anti-imaginary self-dual, depending on the plus and the minus. This solution is known as a no-scale Minkowski solution. Where does this name no scale come from? It has many origins, but it really refers to the fact that, okay, great, you have shown that the potential is like a square, and the minimum is Minkowski, but in fact, you have not lifted all the directions, all the moduli. There are directions in this potential which are completely flat. Okay, so you have a minimum of a potential, but you should think of the potential like a gutter. It's something that still has flat directions, okay, which we call also a moduli space. How can you quickly see that? So here is a quick and dirty way just to see it for some of the moduli. It's clear that in my formalism, I'm not giving you all the moduli of a Calabi-Yau. I'm focusing on simple things like rho and tau. Well, what I've done for you is that I rewrote this potential. I just put something outside. So what I've done, I was careful. I showed you that you can write it as this combination outside. There is a square, and inside the square, you have this combination. So there's tau to the 1 over 2, rho to the minus 3 over 4. And exactly that combination appears here in the denominator. Okay, so you should think of this as one scalar combination. Here is the same one. And here is an orthogonal scalar combination. So you see that in the minimum, this thing vanishes, right? So that means that this scalar field, these combined scalar field directions, have to take a particular value. Otherwise, you cannot make this square vanish. But it also means that this other thing can take any value in the minimum. You see, that means that it's a flat direction. Okay, so that combination of rho and tau is a free field. Let us go back to the 10D viewpoint. Can I quickly see this just from this equation? And in fact, you can. Yeah, and I think it's very cute. So the way this works is if you just eyeball this equation and you realize there's something special going on. I'm taking a 6-dimensional star on a 3 form. Right now, think of rescaling the volume of the 6-dimensional metric. What happens if you do that? The right-hand side is unaffected. There's no volume here. But in fact, also the left-hand side is unaffected. Why? Well, let us quickly check this. And this you can find from the notes I sent in the Skype chat yesterday. So in the Zoom chat. So a 6-dimensional star on a 3 form means that the epsilon symbol will have 3 indices down and 3 indices upstairs, correct? Now remind yourself that the epsilon, well, not a symbol, is the epsilon tensor, it's not a symbol, that the epsilon tensor with all indices down scales like the square root of the determinant of the metric. But if I have 3 indices upstairs, I do that by multiplying 3 times with the inverse metric. So the total metric dependence is schematically like this. I have the square root of the determinant and then 3 inverse metric factors. Okay, now you see it, right? So a volume, what is a volume? A volume just rescales a metric. If I rescale the metric, I have that rescaling to the power 3, and then it's canceled by 3 times the inverse metric. So you see, this equation is blind to the volume of the internal space. Okay, I hope that was clear. And again, this is informal, so please, if there's anything that is not entirely clear, you just ask me, okay? I'm very happy to answer questions. Okay, the last way of thinking about this solution, and this I will need a bit later on, is that there's also a fourth. Yes.
Excuse me.
Of course.
Does the vanishing of the potential at its extremum have something to do with the supersymmetric configuration, or it has
very good question? Name? Yeah, so it's a very good question, and crucially, it does not rely on supersymmetry. Amazingly. Okay. So it's a very good question, and I will get back to this. Actually, I might say so. I will say that now. Okay, I will answer your question using what I wrote on this slide. And if it is not clear, you ask me again. Okay.
Thank you. Yes.
So to answer your question, let us quickly remind us. And I think you might have seen that last week. What are all the moduli, not just rho and tau? What are all the possible moduli? Well, the possible moduli have to do with the complex structure of the Calabi-Yau. You remember the complex structure, what is it? There's a way to combine coordinates, 6 real coordinates into 3 complex coordinates. And the way you combine them is given by the holomorphic 3 form. So in a specific coordinate patch, I can always write it as dz1, wedge dz2, wedge dz3, where the z's are the complex coordinates. And then I have the Kähler form, which is dz1, wedge dz1 bar, same for 2 and the same for the 3rd coordinate, okay? So what are the moduli? The moduli are all the possible ways I can make these combinations, roughly speaking, yeah? Good. So I don't give you the details, maybe you've seen that last week, is that you can actually put the moduli dependence in these objects, in the sense that you fluctuate these objects. And so you should think of this object as getting moduli dependence, okay? So what was shown by Gukov, Fafa, and Witten is that if I compactify on a Calabi-Yau with 3 form fluxes and orientifold planes, then in fact, the 4-dimensional supergravity is governed by the following superpotential formula. It's omega-3 wedge G3. You remember what G3 was? G3 was this complex form I gave you here, right? So this is a complex and even holomorphic expression. But interestingly, it only depends on the complex structure moduli. It doesn't depend on the Kähler moduli. There's no J here, right? And then let me recall you what is the general formula of a scalar potential in terms of superpotential and Kähler potential. So it is e to the k times the inverse scalar metric. Then there are these covariant derivatives on the superpotential minus 3 times the absolute value of the superpotential, right? So let us for a moment call the complex structure moduli phi with an index I and the Kähler moduli phi with an index alpha, Latin versus Greek indices. Then you can show, and this is textbook material, I don't show it for you, that this property holds. It's a very non-trivial property, and some people call this the no-scale property, but that's a geometric property. You can show that the Kähler metric obeys this equation, at least for compactifications to 4 dimensions. So why do I write these technical details? Because I hope you can see something special happening. So, okay, this is a complicated geometrical identity, which you can accept for now. But what should be obvious to you with what I explained to you is that W doesn't depend on the Kähler moduli. So dW, d phi alpha equals 0. Okay, now we're going to use these 2 equations and plug it into here, right? So let us carefully look together. So the indices AB, they run over all the scalar fields. complex moduli and Kähler moduli. And you have to also look at these equations. So what I told you is that whenever the index A is an alpha index or a beta, so a Greek index, this thing will vanish, correct? Because I told you it doesn't depend on the Kähler moduli, but I still have this. So in the Kähler directions, I get K alpha beta bar. I exactly get this combination. You see that? But multiplied with, and this is beautiful, omega absolute value omega squared with a plus sign because it's a square. And then this factor 3 means that it will cancel with this. That is the beauty. This is, so I showed you there's a lot of magic going on here. You remember, like suddenly this thing becomes a square. It's all very nice. In 4D supergravity language, that magic corresponds to this magic. That when I plug it in, I get e to the k. Now only indices in the complex structure directions of this combination. The 3 minus 3w squared is 0. But you see, this is also a sum of squares. Of course, this is our previous sum of squares. This is, sorry, this is this sum of squares, which was in 10-dimensional language, but it became in 4-dimensional language. It became this sum of squares. So what do you see from this potential? Well, to get at 0, it must be that these guys are 0 themselves, correct? So these equations potentially stabilize all the complex structure moduli, but clearly all the Kähler moduli in the Kähler metric, in the Kähler potential, they sit in the front. Clearly they will not be stabilized. They're completely free parameters. Okay. So let us recap. This is the same as what I showed you with the rho tau formula. I say there's one combination that is actually coming to the front and is massless because this vanishes. So this means that, in fact, if you look into the details, this combination you would call a Kähler modulus, and this particular combination would be a complex structure modulus or the dilaton. Okay. Now, with respect to supersymmetry, which was a very good question, you should ask yourself, okay, am I solving the supersymmetry variations here? Well, what are the supersymmetry variations? There is no D term, there's only an F term. And the supersymmetry variations would mean that D of AW is 0 for all the indices. Okay. Well, that would be one condition. But so it's clearly 0. Well, so well, let me be very careful in what I'm going to say now. If you look at the Kähler indices, it would give me this bit, right? So when is it 0? When are you solving the SUSY variations, so to speak, in the Kähler directions? Well, only when W is 0. You see that? Because then this combination can vanish. When is W 0? Let's look at this. Well, it's 0 when omega 3 wedges with G3 so that it's 0. And so what does it mean? It means that, in fact, it fixes the complexity type of G3. What you can show is that, but it's obvious, no? Given that omega 3 goes like dz, 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 you can make this non-zero the moment G3 has a component which goes like dz bar, dz bar, dz bar. Okay, but that is okay. I mean, I can have such a component which is still solving the ISD conditions. So to summarize, the GKP solution, as we call this object, breaks supersymmetry the moment G3 has 3 feet in the barred directions, in the anti-holomorphic directions. Okay. But but there are therefore 2 kinds of solutions: SUSY ones, non-SUSY ones. Okay. And I hope that answers the question. You will see that the non-SUSY ones are in fact the most interesting one. I will come back to that the moment we discuss KKLT. But of course, when we discuss KKLT, if we get there, it's not a problem if we don't get there. Of course, we should discuss quantum corrections, because all I've done are classical statements. Clearly, these are all the 3-level ingredients, but what about quantum corrections? Can quantum corrections lift some of the moduli, the Kähler moduli that sit here? KKLT or large volume scenario claims the answer is yes. And once you do that, the classical Minkowski solution turns into an ADS vacuum. We'll maybe see that tomorrow. Now you should ask yourself the question, can we stabilize all the complex structure moduli using this trick? And this very question, strikingly, I mean, people have studied GKP since the beginning of 2000. Thanks to the Swampland program, people stopped taking things for granted. And what did they discover, which I think is amazing? That for a generic Calabi-Yau, it might actually fail. Okay, so this is, let me try to also use these lectures because I'm very much convinced by the healthy direction of the Swampland program. Let me emphasize this. Okay, so thanks to the Swampland program, people are being much more careful on the technical level and are not taking things for granted. And suddenly we discover after 20 years that stabilization of the complex structure moduli might be less obvious. So what you can do, and this is in the original GKP paper, you can look at very simple Calabi-Yaus, orbifolds of tori, you name it. And indeed, for simple Calabi-Yaus, it works. You can stabilize a complex structure moduli. But of course, the moment people are talking about the landscape, statistics, that means that they are invoking genericity arguments. But the generic Calabi-Yau has an amazing amount of moduli, okay? And then it is shown for exactly Calabi-Yaus with large number of moduli, which we think are the generic case, this can actually fail. I'm not giving you any of the details of this so-called tadpole swampland conjecture. It's state of the art, but please, you can read this paper if you're interested in more, okay? But the rough idea of the paper, I can tell you, without giving any detailed expressions, because myself, I've not been involved, I would have a hard time explaining you the details of that paper. But I do know the rough idea. And the rough idea is that for a Calabi-Yau with large number of moduli, which I told you is a generic Calabi-Yau, we need many fluxes to stabilize them all. And I guess that is obvious to you, no? The more moduli I have, the more flux directions I need to have in order to fix those moduli. But the more fluxes I have, you have to be careful that this number is not growing too much, right? Because for every flux, you could think that maybe the wedges are not dropping against each other. And then this integral keeps on growing. But I told you in the beginning, like, hey, you remember the number of orientifolds is not something you choose. It is fixed by the topology. And that is a problem pointed out by the group in Sackler in 2020 already. Okay. This is state-of-the-art swampland material. Good. Let us go back to our goals. I told you this was a warm-up, but of course I was cheating. This was the most advanced stuff I probably do. And I'm giving it to you. So I showed you, instead of going to the CITRA, I gave you a very famous Minkowski solution. And why? Well, it allowed me to make contact with four-dimensional supergravity, but also introduced to you a very recent swampland conjecture. And what I said in the beginning, GKP, these solutions are the base for lots of string phenomenology. So I might need it for the last lecture, okay? Now let me get back to our goal, which was the Sitter space and scale separated ADS vacuum. And instead of doing an exhaustive analysis, I will give you a few famous, apologies, few famous, very simple examples. So this one is based on a paper from 2007 from Herzberg et al. And they said the following, said, you know what, type 2b is a little restrictive because, you know, there is F3 flux, there is H3 flux, but there is not more. Why is there not more? On a Calabi-Yau, there are no 1 cycles or 5 cycles. So there's no way for me to put F1 or F5. So they said, why not go to type 2a on a Calabi-Yau? Because then I have, you know, F0, F2, F4, F6, it's all possible, and H3. And the typical example that we try is we say, okay, in type 2a, we use orientifold 6 or D6 brains. Of course, there is much more, but these are like the vanilla models, which have been understood and people understand well. And I told you we're working on a Calabi-Yau, so that means the internal curvature is 0. Of course, at this point, you should ask me, Thomas, why are people doing this? Why is always Calabi-Yau? And I agree with you. It's weird. But there's a technical reason. For Calabi-Yaus, we have the technology to do the computation. That is one. And we can actually go beyond supergravity, okay? String theory on Calabi-Yaus is actually something that is being developed and has a long history, all right? So this is a particular reason we do that. I mean, let me say a few more words on this. So the thing you really want is control over your calculations, right? I mean, I showed you in the beginning. And one way to get control over the effective field theory is if there is supersymmetry. At least supersymmetry of the Lagrangian. That's different from having supersymmetry of the background solution. If there is supersymmetry of the Lagrangian, but the background solution breaks supersymmetry, the effective field theory is still supergravity on one condition. Namely, the SUSY breaking scale should be well below the Kaluza-Klein scale. So the hope of sort of the supergravity / string theory community is that compactifying over manifolds that lead to 4D supergravity, we can consistently do it. And when we find solutions, vacuum solutions, which are phenomenological and therefore break supersymmetry, we go back and we quickly check that the SUSY breaking scale is well below the Kaluza-Klein scale. And it means that indeed our assumption that the 4-dimensional theory was a supergravity theory was a good assumption. Why do we like supergravity theories? In the old days, people said, oh, naturalness, we need to solve the Higgs hierarchy problem. So we think, in LHC, we will soon find supersymmetry. That didn't work out. Maybe, there's still some hope. I don't know. It naively doesn't look good, no? But there is another reason, which is technical, as I just told you. The moment your effective field theory is a supergravity, well, the couplings in the Lagrangian are very restricted by the supersymmetry algebra. The number of fields is very restricted. And that is what I mean with having control, okay? Good. So let us do that. Let us use, one more comment, sorry. Does that mean that we always have to use Calabi-Yau? The answer is no. What you want is a manifold that would allow a non-vanishing spinner. Okay, so the general language is that you need an SU3 cross SU3 structure manifold, in case you know that. But in the particular case of Calabi-Yau, we really have much more tools developed. Okay. Anyhow, that's enough blah blah. Let me get back to the computation. So let me again just ask these two typical conditions, that the variation with respect to rho and with respect to tau vanishes. And if I do that, I get the following two equations. Now, this is a little bit more work, but let me quickly check at the second equation. I know that VH is positive, and I know that all these flux energies are positive. So the only way I can get 0 is, again, if the source itself is negative, so -3 times the source energy is positive. So again, I need orientifolds. So please try to, see how important orientifolds in this are, right? You just see that with these ingredients, the only way I can have a solution is if the orientifolds are there and they dominate the tension. With some algebra, which you can do at home, you can manipulate this expression and you find that the on-shell value of the cosmological constant of the scalar potential is given by this equation. Since V2, V4, and V6 are all positive, this is strictly negative. So I learned that the moment I have these fluxes, I have negative energy. I have ADS vacua. If I want Minkowski vacua with these ingredients, well, I need F2, F4, and F6 equal to 0. Okay. What about tadpoles? Before I showed you the tadpole used in GKP, now there is again one. The equation we have is dF2 equals F0 wedge H3 plus Q times the source, right? So the same trick tells me that if I integrate this equation perpendicular to my O6 planes, this is my constraint, okay? And again, this number is fixed by topology, and it cannot be taken too large. And along these lines, then one can show very simple, okay? So using the two previous equations, I can show that if there would have been no negative tension, I could still have solved these equations, but then I would have had to drop this condition. Okay, using these kind of manipulations, I can still remove this guy, but I would need a positive curve geometry. This should ring a bell to you. Given the first lecture, the first example, which was Freund-Rubin, I showed you that if I take a manifold without orientifolds, blah, blah, and I put fluxes, the Einstein equation is telling us that these fluxes back react on the internal manifold and it curves them in a positive way. They become like sphere-like objects. right? In this language, you see that, namely, if you don't put the curvature energy, you cannot solve this equation. It's the same thing. So you can ask yourself, hey, but then why is it possible to actually, what is wrong with the argument of the Einstein equations? That if I fluxes, they backcorrect and they should curve the manifold. Well, you have to be careful. The moment I have an orientifold, it has negative energy. So it backcorrects on the manifold in exactly such a way as to cancel these positive flux energies inside the energy momentum tensor. This is why you can have fluxes on a Calabi-Yau space, at least globally. Okay. Another thing you can do with trivially just manipulating these equations, I mean, it takes you, I think, 10 minutes maximally, if even that much. You can see that the Sitter vacua in type 2a are only possible if I have O6 planes, if I have negative curvature. So the internal manifold has to be negatively curved, which means VR is positive. And so as I said, the source energy should be negative, so it should be orientifolds, not d-branes. And the Romans mass is non-zero. Let me recapitulate this, right? So what I can show is that this setting discussed by Herzberg et al., there is no de Sitter solution, despite having all these ingredients. Because the potential I just showed you is negative, it's ADS. So what you have to try to do is to go beyond, and the answer turns out to be, okay, I can flip this sign on the condition that this becomes a negatively curved space, so no Calabi-Yaus anymore. And I keep the Romans mass and I keep the orientifolds for sure. Okay. Does it mean that there is a solution? No, I just gave you necessary conditions. I stabilize with respect to two fields. generic space has many fields. So I need to do much more work to show that I can get a solution, but this was at least a necessary condition. Okay. So let us try to prove these statements, okay? And let us also make a link with the Swampland program. So before I do that, I want to add one more detail, which was the whole point of this paper, which is a very pedagogical paper. You can do more than what I did. Okay, what I showed you here is that, okay, if there is a vacuum, it must be ADS. What they have shown is that also slow roll would not be possible. So they say, look, let us take this potential and look at regions in parameter space where the potential is positive and not negative. I know I don't have a vacuum, but it could be run away, and it could be very slowly run away. And they've shown that the inflationary slow roll parameter, in fact, has to be larger than 27/13. So that doesn't work. In case you don't remember what is the slow roll parameter of an inflation, in a multi-field case, this is a formula, okay? So it's like the square of it is like the double derivative is like the derivative of v squared. Here is the metric on the scalar space divided by the potential. So this means that this model, there's no de Sitter, but there's also no inflation. Okay, and in fact, this is true for many classical flux compactifications. You can show in many cases, but not all, that epsilon always has to be larger than order 1 with these kind of little tricks that I gave you. Okay. So how is that consistent with the results in the literature? In fact, I quickly want to remark this before I might, let me see what is near the end of what I want to say. Okay. I made one mistake. I told you that we will, no, it's an exercise to prove these two statements. Yes, I thought I would tell you this. No. It's an exercise to prove these two statements at home. And as I said, it takes you probably 10 minutes or less, but please try to do this. Then I think you really have a feeling you understand it. Okay. So I just told you these are all necessary conditions and so on and so on. But of course, in the literature, people did much more than these simple exercises, okay? So they said, okay, we have found a go. So what you could call a no-go is this. The no-go is the one by Herzberg, says with these ingredients, no de Sitter. And what I call a go means that, hey, with these conditions, negative R6, Romans mass, orientifolds, we cannot derive a no-go. So we call that a go. And then you try, okay? And this was done in many papers starting in 2008, in which I was involved as well. And I can tell you what is the results of all that work. And there are many papers, especially David Andriot and collaborators have done a lot in the last years. But I think, and I hope he would agree, that it's fair to summarize all of these papers in a very simple way. Nobody found a de Sitter critical point at parametric with coupling and large volume. So this is bad news in the sense that it's bad in the sense that none of the de Sitter we found de Sitter critical points, which the first time I did this, we were amazed, like, wow, we actually have a classical de Sitter solution. But then you look into the details and we found no, GS is order 1, the volume is only order 1, so you should never trust this as a string theory solution. And even worse, even if you would close your eyes and you say, maybe I'm okay with GS order 1, and maybe, you know, the volume order 100, I'm kind of trusting this. Even then, we always found tachyons, always. So the status is unclear on this whole topic of having de Sitter solutions in the classical regime. You can wonder, you know, is there a proof of these statements? Because of course, what we did and what David Andriot did was taking simple examples. You know, what about more complicated examples? Well, of course, at some point you should stop trying examples and you should try to understand why you find what you find. So let me not say too much. I don't think there is a proof that always are tachyons, but at least there is an understanding why they're often there. If you're interested, you can read this paper. And then there are arguments, and to me, they are important for the Swampland program. This point is super crucial for one of the Swampland conjectures. There are, in fact, supergravity arguments why small GS and large volume is unlikely. And there are 2 highly pedagogical, very simple papers, which you can read from the beginning till the end with all of the technology I've gave you in this lecture and the previous one. And they explain how this works. And what I can do in the last bit of this lecture is to only sketch a proof, which is extremely hand-waving, so it's not a full proof, but it at least gives a flavor of what goes wrong, why you cannot get small GS and large volume, okay? And I'm only like taking like 1 paragraph out of these papers, and of course these papers are much more detailed, okay? So the proof works as follows, or the sketch of the proof. I just told you that in type 2a, we need orientifold planes, negative curvature, and Romans mass at the minimal ingredients, okay? We also know that F0 and H3 are bounded by tadpoles. So you cannot crank up their numbers. But we also know that F4 is not bounded by fluxes, by tadpole conjecture, by tadpole constraints. So maybe what I need to do is to take a number very large, right? Because I showed you before, like for a Freund-Rubin solution, the only way to get like small curvature is to take some flux quantum and send it to infinity, right? But maybe we can do this for F4. So let us try to check this. So let us say that there's a 4 cycle. This is the flux quantum n, and we send n to infinity. What does that mean? It means that V4 contribution will scale like n squared, right? It goes like f squared. So the n goes in a square. And this is the rho tau scaling, which we have derived before. We still have the old expressions VR going like this and VO6 going like this. Okay, and we say, okay, let them not scale with n. Why? Well, clearly orientifold tension cannot scale. It's just a fixed number by topology. All right. And now what I'm going to do is I keep this in mind, and I'm going to demand that the potential has the critical point, but I do send n to infinity. And you could say, but Thomas, we have been playing these games all the time, like just looking at d rho, d tau equals 0. What? It's a little bit more tricky now. Because if I really want to send this to infinity, the only way that these terms in the potential can balance with each other is that all of them have a non-trivial scaling with n. Is that clear to you? I mean, if you just look at the potential, if this goes to infinity, and if you want the minimum, then this must balance against this and this, they all have to scale with n to some power, right? So I say, okay, this must mean that on like the critical point must be such that n, the rho scales with n to some power a, and tau n to some power b. So what I fill in is I'm just filling this in here, and I'm not taking any derivative. I'm saying, look, if you get a minimum, is because terms balance against each other. So that means that they almost have exactly the same scaling with n, right? So the scaling with n of V4 is this expression. The scaling of VR with n is then this expression. And this is true for VO6. So how can they all scale in the same way? Well, I get all of these constraints. I get this has to equal this, and this has to equal this. These are 2 equations. But you see that this, wait, I must be making a mistake because I just told you that I know that these equations are impossible, but I have 2 equations for 2 variables. So what is going wrong? Okay, I made a tiny mistake, and I know what it is. My apologies. So this is an exercise for home. If I didn't make a mistake, so asking that this scales with this is one equation, and asking that this scales with this is another equation. So I have three equations. So I have two equations for two variables that fixes them uniquely. So I must have made a mistake here. So what was the answer? If I remember correctly from the paper, I was probably too quick when I wrote the slides, is that if you then check what the scaling is, you find that the scaling sends you to strong coupling. So there's no solution. Okay. So please try to check what I did wrong here at home. I would appreciate this. Thank you so much. I think I have 2 more minutes. And in these last 2 minutes, let's see how far I can get. What we can do is I can finish this lecture by telling you what is a swampland statement regarding these things. And then next lecture, we can start with the heuristic proof of this swampland criterion. And we go to scale separated anti-de Sitter vacuum. Okay. So what have I been doing? We have done very simple supergravity exercises. And we found that, you know, and I told you also about the literature. So it looks like there will be typically strong coupling if you can find the Sitter vacua with classical ingredients. So by classical, I mean fluxes and orientifolds. And in fact, this inspired what is called by now the de Sitter swampland criterion. And I think it's often completely misunderstood. So let me make it very precise what the criterion is saying. The criterion is saying that in asymptotic regimes of field space, and keep in mind, this is in the asymptotic regimes where I can trust, if you like, you know, classical reasonings, we must have that the gradient of the potential is larger than an order 1 number times the potential, or the smallest eigenvalue of the Hessian is bounded by this number. So C and C prime are 2 order 1 numbers, and they're positive. And imagine this is true statement, then you already see why the Sitter is impossible, I guess, right? So this is an OR. So imagine, okay, this clearly rules out the Sitter. Why? For the Sitter, I need this to be 0. I need a minimum or an extremum. And this is a positive number, and this is a positive number. 0 cannot be larger than positive. And it would be say, oh, but imagine I can still do it. Then I must have a tachyon. Okay, you could say that is consistent with the literature, but my point that I want to push is no. In fact, the literature on this topic would be okay with only this conjecture, because we have not ever found the classical de Sitter unstable solution in parametric recoupling and large volume. Okay, by the way, a very technical remark. To make sense out of this expression, it means that I went to a filtered definition at the critical point where the scalar metric can be diagonalized into the identity matrix. Okay, as I said, and then I finish my lecture. This is consistent with the literature. And then you can wonder, okay, but where did this come from? Okay, I can tell you this is a technical remark that was needed in this paper, well, in a follow-up, no, in this paper in order to make the logic, to make the reasoning. But I think it was also motivated by a nice example, which was pointed out by Hebecker, Denef, and Raza. And they said, hey, wait a minute. If this is the only conjecture, aren't we in trouble with the Higgs? Because clearly, you know, the standard model exists. And, you know, we live in, you know, the minimum of the Higgs potential, but, you know, it's a Mexican head. Clearly in the middle, there must be some kind of a de Sitter space. But okay, the de Sitter space is tachyonic, so it's in that sense not a very phenomenological de Sitter space. Okay, what I will do next lecture is I will sketch a heuristic proof of this. But let me make clear, this is state-of-the-art swampland. This means, and especially these swampland conjectures are the least rigorous of all. So you will see that whenever I say a proof, it is really extremely heuristic, and you can maybe easily punch a hole in the argument. But let's see, I will sketch a proof next lecture. And when that is done, I will move to anti-de Sitter space. okay, for the next lecture. So I would like to ask you if you, in case you have any questions about what I've been saying.
Okay, thank you very much, Thomas, for
You're welcome.
very nice talk. Yeah, we have time for questions. Please raise your hand if.
Hey, I might have a question.
Okay, yes, please.
Yes.
Yeah, since the Swampland program somehow wants to make statements about all quantum gravity, not only string theory, is there evidence that the de Sitter Swampland conjecture also might hold for other UV completions besides string theory?
Right. I think that's a very good question. And my answer will not probably satisfy you too much. So in order to ask such a question, you need at least an alternative to string theory that is sufficiently developed in order to make, computations and statements, and very quantitative statements. Okay. And to me, that is actually very unclear that is even possible. Right. So for instance, and I'm like zero expertise on loop quantum gravity. I only have some information, say, about from talks. One of the open problems in loop quantum gravity is whether what is the vacuum? Can we even get to something like Minkowski space? Right. So I don't think, or somebody else should correct me, it looks like maybe it's not sufficiently developed to actually be able to make such statements.
Yes, thank you. And then a second question on the same topic is there evidence inside string theory for the de Sitter Swampland conjecture or other things that are not based on Calabi-Yau compactifications?
Yeah.
So Calabi-Yaus are very special manifolds.
Absolutely. So this is a very good question. So yeah, exactly, yes. So what I tried to tell you is that, okay, you could say that KKLT, etc., is based on Calabi-Yaus. And again, don't. It really is for computational control. Okay, so that's why it was invented. But all the examples I gave you here. Okay, here I summarized literature, but this literature, I told you from the beginning, never works with the Calabi-Yau. So we went around this no-go by actually looking at negatively curved internal manifolds. Okay, so we did. So all of the literature quoted here, none of that is with Calabi-Yaus.
I see.
Yeah.
Thank you.
Also, in this regard, I want to mention, for instance, recent work by Eva Silverstein, which is very interesting. She really we still use manifolds that allow a supergravity description in the sense that they're what we call, SU3 structures. She now has a program to try to construct de Sitter solutions using hyperbolic spaces, which are compact. And they break supersymmetry immediately at the Kaluza-Klein scale. So that's really getting really far away from this vanilla Calabi-Yau limit. Okay, as she claims it works, but I think we still need to, the community still needs to settle on this. Yeah.
Okay, any other question?
May I ask a question?
Yeah.
Comment?
Yeah, sure.
Yes.
Excuse me. Are there sort of criteria or rules to choose the brain, to select the brain setup for doing this story of flux compactification?
It's a very good question. So not really. What I would advise you, I've done it in a few papers, is that you play these rules, these little tricks I showed you with this rho and this tau, and that should guide you. Okay. What I did notice is that in the literature, we like to not make it too complicated. And so most of the no-go results that exist always invoke one kind of source, right? So say a bunch of orientifold 6 planes, but it seems to me, I kind of moved in another direction, but if people are interested in following this program, so one thing which I think would be very worthy of trying is to really do the mixed case. Like, I don't know, I have a 04 or 6, and in particular has been suggested by Kachru et al. That NS5 brains are the thing to use. But with NS5 brains, I have a problem is, you have to be extremely careful with the tadpole, because an NS5 brain is a magnetic charge of the H field. So it's like DH equal delta. So how you solve the tadpole in that case? So the only way to solve the tadpole, it gets very technical. If it's the NS5 brain is wrapping a contractible cycle so that it doesn't induce any charge, but it should do so in such a way that it's not unstable. Okay, this is highly non-trivial to do. So, yeah.
Okay, thanks.
Okay. And
Mahdi?
then,
Okay, sorry. Yeah.
Excuse me. Can I ask another question?
Yeah, sure.
Can this story of flux compactification be done in a more simple model, like, for example, in 11-dimensional supergravity, which has only one form field? Can it be extended to?
Very good question. So I think having multiple forms is a good thing. It's not a bad thing. It's clear from what I explained that the Sitter space, if you want to get it, if you think you could get it, it clearly involves many things. So that's the main lesson we learned is it's going to be dirty and complicated. So the main problem with 11-dimensional supergravity is that there is no orientifold plane. And I didn't explain you the famous result by Maldacena Nunez because it's kind of incorporated in what I've told you, but I tried to tell you I need negative tension. Of course, there is a way to introduce negative tension in M theory by using derivative corrections or specific kind of singularities, but then life gets really complicated. So yeah, it's not easy. Yeah.
Thank you very much.
You're welcome.
Okay, Mario.
Yeah, thanks. Thank you very much, Thomas, for this very nice and clear lecture. I have a more, I have a question more into the physical meaning of, for example, the de Sitter Swampland conjecture. So, assuming this is true, yeah, how can I interpret this conjecture that string theory cannot explain, for example, inflation? So inflation is only an effective field, an effective theory that cannot be explained using string theory, or
good question.
How should I
so
interpret, for example,
this is why I
conjecture?
emphasized in the beginning that I showed you the de Sitter conjecture. I want to emphasize it's set in the asymptotic regime of parameter space. All right, so this conjecture doesn't rule out de Sitter in the more difficult part of parameter space. Okay, de Sitter could be maybe like quark confinement, something that we just don't get, or with current technology, it's very difficult to get an analytic handle on. Okay. So that is one possible scenario. Another scenario, which I think is so what Vafa has in mind, which I sympathize a lot with, is that, well, and now I'm giving you my, when it comes to inflation, my opinion. I think inflation, to me, a huge problem from the start is that we're insisting on trying to understand the initial conditions for the universe in the language of 4D effective field theory. This is, first, we knew in advance this was dangerous because we're getting close to the Planck scale with inflation. That's one. Secondly, there are all these, naturalness problems in inflation. Think of the eta problem, which is shouting to us that, we're really on the edge of controlling effective field theory. So you don't need string theory for that. But from a stringy point of view, it's the most bizarre thing ever for me to think that inflation would be describable in 4-dimensional effective field theory. Why? Inflation is telling us what's happened to the very early universe and how it went to its vacuum state. Right? If I put my stringy hat on and I think of extra dimensions, I could say, wait a minute, why is inflation not like some dynamical transition in which the universe decided, I don't know, maybe it was like, in case you know the Brandenberger-Vafa scenario, it was like all dimensions were small, literally all spatial dimensions were compact, and it decided to suddenly make 3 dimensions grow. If that is a scenario, this you don't describe using 4-dimensional effective field theory, no, because the universe was in fact 1-dimensional at early times, right? So you would have to use topological theories or totally different things. But so saying inflation is 4D effective field theory is getting you in trouble from the start, because you really want like, oh, extra dimensions are stabilized and they're small, and then I want some other directions to suddenly flow into the vacuum. to me, that just sounds very bizarre. Why? I mean, I know why we want that, because we can compute, but that is not a good argument, right? Yeah.
Yeah, absolutely. Well, thank you very much.
You're welcome.
Okay. Mahdi, I think you also have a question.
Yes, maybe I have a
Okay.
quick question. Thanks, Thomas, for a great talk.
You're welcome.
Actually, the second statement of the de Sitter conjecture, does it apply in the everywhere in the moduli space or just in asymptotic regions? Because
I would say asymptotic regions, yes.
Because for the case of Higgs, the Mexican has kind of potential. It's not asymptotic, right? It's in the middle. It's actually
It's a very good point. You hit the nail in the right spot. So yes, I agree. So I have to be. I mean, I meant it more as a motivation, right? So, but I would say that that's what we also have to be careful what I mean with parametric regime, because it would be in terms of the string variables, the asymptotic regime, right?
Not in canonic basis, you mean?
Sorry?
Not in canonic basis.
Right. So it could be like in terms of string fields, maybe the minimum is, I don't know, like the middle of the Higgs potential could be actually, I don't know, in another regime. But actually I shouldn't advertise my own work, but I have a paper where we actually speculate about the minimum of the Higgs potential using a Swampland criterion, which I actually believe could be very well correct, which is called the Fessina-Lente bound. And yeah, you can always look at that. It actually says that indeed a cowboy hat would not be allowed. So the minimum should be a tachyon, in fact. Yeah.
Actually, as far as experiments go, we don't know what if we have a Mexican hat potential, right? We haven't proved that part of the potential.
Absolutely.
So it's
not,
yeah.
It's experimentally at the moment, we haven't probed that region at all. I totally agree. It's actually highly sensitive to to irrelevant operators of the standard model. So yeah, yeah, absolutely. Yeah.
You may tell us tomorrow why we need then the second statement for the Sitter conjecture, because Higgs, I mean, the Mexican has in the, we don't need to survive with the Mexican hat potential.
I agree.
Right?
It's a better, I agree with you that if you just follow the words that I said, it was not very convincing. I think I was giving you more like the historical line of why this, and then of course in the paper that I showed by Palti, Oguri, Vafa, and Shiu, they did need it though in their proof. But I will give a simplified proof by Hebecker et al. Where that condition is not really discussed. So I don't have a strong opinion. What I do have a strong opinion on is when people say that this condition of the tachyonic condition actually came from the work on classical de Sitter vacua in which I was present. I disagree for what I told you. So in that work, we have no example where it was at weak coupling. And it's true that all our solutions are tachyonic, but the statement made by Vafa, it says or, right? So I don't think you can use the arguments of the literature of classical de Sitter vacua to argue for that second statement. Yeah.
And about that overshoot problem that you mentioned in Calabi-Yau with many number of moduli fields. So is it specific for Calabi-Yau flux compactifications? Because for the case of M theory and G2 manifolds, we can have G2 manifolds with large Bethe numbers, and we can use non-perturbative effect like Gauge condensation to stabilize all of them without any overshooting problem. So can we use that idea? I mean, Gauge condensation in Calabi-Yau.
I think you asked the perfect question. So I think you're referring to the work, say, also of Gordy Kane and Bobby Acharya.
Exactly.
Which has not been discussed in the Swampland literature, unfortunately. So I don't want to make a strong statement, but the argument would be that I can only tell you what would be the intuition of some of the people working on the Swampland, is that these constructions are highly between bottom up and top down. Like to claim that we have real top down understanding of G2 manifolds with all of these non-perturbative effects, I would say we don't, right? So it's also based on genericity arguments, and it's very difficult to check them in detail. But in fact, it could. I wonder if you apply the most recent paper by Vafa, which has a holographic interpretation. My naive guess is that these G2 manifolds would be in trouble. But I have no strong opinion. This is beyond my expertise, to be honest. Yeah.
Thanks. Thanks.
Welcome.
Okay, thanks again. Somebody has asked in chat.
Oh, sorry, I didn't see that.
Yeah, if it is possible to have the lecture notes.
Yes, if everything went well, but these are emails with a lot of, I send them to Majdi, who might have seen them. Yeah, I actually did send it.
Yeah,
and if it doesn't work, let me know.
I will upload on the web page.
Okay, perfect. Thank you.
Okay, fine. Thank you very much again. So we will see you tomorrow for the final lecture.
All right, perfect. Thank you.
Thank you.
Have a good day.
We will back in 10 minutes.